Fine. Okay. So if you remember last class, like we considered 2D maps, right? So maybe I will just give you an overview, right? I will just give you an overview what have we have been discussing since last class. So we discussed 1D maps before, and in 1D maps you were only having one variable. You can see from here, you were having only one variable here, that is x. Fine. And what happens to that? You can see that only x will change. Like x can be positive or x can be negative. So it only varies on a number line. So this is the number line you can see over here, right? So you can see on the right side of 0, there is on the right side of 0, there is a positive values of x. On the left side of 0, there are negative values of x. So therefore, that is the only freedom the variable x has. Either it can go right hand side or left hand side, right? I mean, it can jump to the left, it can jump to the right, those it traits. Other things it cannot do, right? Or more freedom it doesn't have. Okay. So you can see that why in 1D maps we can still have attractors, right? Why? In 1D maps also we can have attractors. What is the reason behind it? So you can see that suppose you take this case over here, it's a period 2 orbit. Why? Because you can see that one iteration from -1 going to +1, and if you iterate that point +1 again, it is going to -1. So therefore, from -1, it is repeating in between -1 and +1. So therefore, it's a period 2 orbit, right? So you can still have chaos. You can still have chaos. In that way, 1D maps are very nice. 1D maps are very nice. Why? Because 1D maps can show chaos. Can 1D flow show chaos? No. Can 2D flow show chaos? No. 2D flow also cannot show chaos. Okay. Can 3D flow show chaos? Yes. So for flows or a set of differential equations, you need to have a minimum dimension of 3 to have chaotic dynamics, right? So therefore, many of you are working with the continuous systems or maps, right? Maybe are you working on 2-dimension or 3-dimension? 3 dimensions, Rosler, right? So therefore, why this is understanding that why 3 dimensions? Why not 2 dimensions, right? Because in 2 dimension you cannot have chaos. I mean, 3 dimension is the minimum in your ordinary differential equations or a system of ODEs where you need to have chaos. But for maps like xn plus 1 is f of xn, you don't have to worry about that feature. In 1D maps itself, you can have chaos. In 1D maps itself, you can have chaos. So that's one of the best understanding and simplicity of 1D maps. Okay. So you can see in 1D maps also you can have chaos. You can have a fixed point that is x star. That means if you start at x star, you stay at x star, right? Okay. So why we have to go to 2D maps? I mean, if 1D maps have periodic orbits, if 1D maps have chaos, if 1D maps have everything, then why do we have to go to 2D maps? So that's one of the reason we will, I have not covered in the last lecture, but we will cover here. What is there in 1D maps? What is not there in 1D maps that the 2D map has? Okay. So that's the part of the study we will make in today's class, and is one of the most important and very basic understanding. Okay, one of the most basic understanding. So yeah. So you can see these are the 2D maps, like how 2D maps looks like. So 2D maps looks like this, right? Xn plus 1, Yn plus 1. And you can easily see over here, right? That Xn plus 1 is F1, F1 of Xn, Yn, and Yn plus 1 is F2 of Xn, Yn, right? So these are the two variables. Now, one thing which is important in 2D maps and not present in 1D maps is in 2D maps, you can actually visualize things, right? In 2D maps, you can visualize things. That is how in variation of both X and Y things are changing, right? So this is what I gave to the class last time, right? And I suggest the class to do it now also, okay? I suggest the class to do this now as a Python exercise, okay? What to do? Create two arrays X and Y, give their initial condition as say 0.1, 0.1, okay? And iterate the map. This is the mapping. This is the mapping here, okay? Iterate this map for say 10 to the power 4 times in a loop, in a for loop. Iterate this map 10 to the power 4 times. And every time you iterate, you have a point. You plot that point on the XY coordinate. Okay. Can you do this and tell me how the shape looks? Yeah. I think we did this in last class. Okay, we did this in last class. So try to do this exercise. Okay. Then we can go forward. Okay. So you can see that this is the attractor here, right? This is the attractor here. And it's a very nice attractor. Why? Because when you zoom to this region here, then you get this figure. Okay. And again, if you zoom this figure here, you get same figure here. This is the zoom of that. Again, if you zoom this part, again, you will get this figure. So you can see that whenever we zoom in, the structure remains similar. I mean, those set of lines and dots you see. So therefore, this is a fractal. Therefore, this is a fractal, whatever we have covered in the previous class. And that map was devised by Henon. Okay, that map was devised by Henon scientists. So it was known as a Henon attractor. Okay, that attractor is known as a Henon attractor. Now today, this class, we will be learning a bit more about this attractor. Okay. So, but yeah, and after that, I will tell you, you should remind me that why we need to study 2D maps if there is already 1D maps. If in 1D maps, we see periodic orbits. If in 1D map, we see chaotic attractor. If in 1D maps, we see fixed point, then what is the need to have 2D maps? Okay, what more 2D maps can offer to us? Okay, but before that, let us understand the dynamics of this map. Okay. Okay. So Henon map. Okay. Henon map, right? So it's a 2D map. So it was developed by this French scientist Henon. Okay, who devised this parabolic square term map, nonlinear, right? Can you tell me what is the equation of the map? Xn plus 1 is equal to? Xn plus 1 is equal to? Hmm? Xn. Yn plus 1 is equal to 1 plus Yn minus Axn square, right? Yeah. Is it fine? This is the 2D map. Okay. Is it correct? Correct, right? Hmm? Okay. So this is the 2D map. Now, how we can analyze this 2D map? That is the question. Note that when you note that when we started working with 1D maps, how you found stability? First of all, how you found fixed points? You did x star is if xn plus 1 is f of xn for a 1D map, for fixed points, you did x star is equal to f of x star, right? And then you found the solution to this equation, right? And how do you know whether this fixed point is stable or not? If the derivative of the fixed point at x star, the absolute value is less than 1, then x star is stable, right? Else x star is unstable. Is it okay? Fine. Fine. Agree. This is all about 2D maps. This is all about 1D maps. Now my question to you is, how can we analyze this 1D map? Okay. Huh? Yeah. I think we flipped it, right? Okay. Can you tell me again? Xn plus 1 is equal to? Yes. So this, hmm? I think that was one part of the map. We were doing few transformations. That was one part of the transformation I wrote. Okay. So this is the final map. This is the final map. We did some rotation, stretching, and all those things. Okay. So this is the 2D Hanon map. Now my question is, what should we do? Now, one of the question is the map invertible. This is the first question. Question one, is the map invertible? Is the map invertible? What do you mean by invertibility? And why we need it? I will tell you. Okay. So is the map invertible means that for a given xn plus 1, yn plus 1, has this value come from one value of x and yn or multiple values of x and y? You understood? Like x square is not invertible. Why? Because minus 2 and 2 gives the same result 4. So therefore, for given xn plus 1, yn plus 1, what previous values of x and yn are there? Is it a unique value x and yn, or there are multiple values of x and yn for which you are getting xn plus 1, the same value of xn plus 1, yn? Right? What do you think? Is this the map invertible? I mean, can you find for a given xn plus 1 and yn plus 1 unique x and yn? If you find, then the map is invertible. Else the map is not invertible. What do you think? What do you think? Hmm? So this is one of the question I want you to answer. Okay. What do you think? What do you think? For a given xn plus 1 and yn plus 1, for a given xn plus 1 and yn plus 1, we have unique values of xn and yn. We have unique values, right? Isn't it? So these values you fixed, right? Xn, this yn plus 1 and xn plus 1, you fixed, right? Now when you fixed this, A and B are already fixed, right? So you get unique xn and yn. You get unique xn and yn. Okay, fine. But there is also another theorem, I don't know if you remember, that if your map is invertible, then determinant should not be 0. Okay, I hope you remember this. Maybe in your real analysis later, but I mean, this is a bit of hard theorem, many might not be knowing, but determinant also plays a role. Okay, determinant. So determinant of whose? Determinant of the Jacobian matrix. So can we consider the Jacobian matrix for this? Jacobian matrix. So Jacobian matrix J is nothing but, you can say dou xn plus 1 by dou x and dou xn plus 1 by dou yn. Okay, dou yn plus 1 by dou xn, dou yn plus 1 by dou yn. Okay. So if you do this, can you tell me? So what you have to do? You have to just take this part. You have to take just this part and differentiate it with respect to x and y. Okay. So what you get when you differentiate this with respect to x? Yeah, minus 2axn, and with respect to y you will get 1. Then let us come to this part. So here you will get b, here you will get 0, right? So what you are getting? The Jacobian, the determinant of Jacobian you are getting as minus b. Okay, minus b. Now, if b equal to 0, if b is equal to 0, then you have a problem. If b equal to 0, then you have a problem. Why? Can you see why you will have a problem? B is appearing in the denominator here. Okay, so you can clearly see a link between this quantity and this quantity over here. Okay, there is a link. Okay, there is a link. So if b is 0, then you can see the denominator is getting 0, right? Okay with that? So therefore, if b equal to 0, then you will have a problem with invertibility. So b equal to 0 is the only point where you will have a problem with invertibility, right? If b is not 0, this map is invertible. If b is not 0, if b not equal to 0, the Hannon map is invertible. So Hannon map is invertible, right? Any doubts with this? Is okay? So you understood why we are calculating determinant. So first of all, is the map invertible? So what we know, keep the xn plus 1 and yn plus 1 as fixed. Then check whether are you getting unique values of xn and yn, right? Are we getting? Yes. How? You just have to write xn and yn in terms of xn plus 1 and yn plus 1, right? So how can you write? Yes, xn is equal to yn plus 1 by b. Isn't it? This you got, right? Fine. And can you write from this equation about yn? Yes. Yn is equal to xn plus 1 minus 1. Minus 1 goes this side. A also goes that side. But a xn square. Xn already you have yn plus 1 by b. So therefore you can put it. Now whatever value of xn and xn plus 1, yn plus 1 you fix, it will give you unique xn and unique yn. So therefore the map is invertible, right? But you have a problem because b is coming in the denominator. If b is equal to 0, then you are running into trouble. Then these pre-images are going off to infinity, not defined, okay? And you can see that exactly you saw why that is the case. Your map is invertible. There is a condition that if your map is invertible, determinant of j won't be 0. If a map is invertible, this is a theorem from analysis, okay? If a map is invertible, there is a relation between invertibility. If your map is invertible, if map is invertible, implies determinant of the Jacobian is not 0, okay? This is one of the theorems, okay? This we used. So what we did, we computed the Jacobian and we computed the determinant. When we computed it, we came to know that determinant is nothing but minus b. So therefore, you can easily see that if b is 0, then determinant is 0 and hence non-invertibility is lost. And that you can clearly see from this example also, right? So therefore, for b not equal to 0, the Hannon map is invertible. So we answered this question. Now, even though, let us go to the next one. Okay. Even though, like you can see, we have computed the Jacobian, let us make use of it. Now, what does Jacobian suggest? What does determinant suggest? Do you guys know what is the geometrical interpretation of determinant? What is the geometrical interpretation of determinant? From your class 12th, you might be remembering. What is the geometrical interpretation of determinant? But geometrical meaning. It represents area. Determinant represents area, right? Determinant is nothing but modulus of A cross B. If there are two vectors A and B, then determinant will capture the area spanned by this parallelogram, right? That is the determinant, right? Agree? Okay. So we will know whether the map is contracting or expanding. What does it mean for a map to be expanding or contracting? This we discussed in last class also. You see this, that if you know a 2D map takes a 2D point to a 2D point. Do you agree? What does a 2D map does? This is X, this is Y, no? If you have this one point here, this is, if you apply the 2D map, this point will take to another point, right? Yes. So a region, this is a region, right? This is a region. This is a region. Do you believe that this region is made up of a million of points? Yes. So if you apply the map to the million of points, it will map to another million of points. If it is mapping to another million of points, it is mapping to another area, right? So an area is getting mapped to another area under a 2D map, right? So therefore, you can see that this is n, right? This is n over here. This orange region here is n, right? So when you apply the map f to n, the 2D area, it became this green area, that is f of n. But what is interesting in this? The interesting part here is f of n is lying inside n. F of n is lying inside n, right? F of n is a subset of n. So this is contracting. This is contracting, right? You understood the idea, no? You understood the idea. So you have a bigger region. When you apply the map, it got contracted inside, lying inside. So it's a contraction. So in that case, we call F to be a contraction mapping. Similarly, when you have a n here and you apply the map F and you clearly see that it has gone outside the region, then it is an expanding map, right? But here in the third case, it is very interesting. Why? Because it is neither contracting nor expanding, right? Because you can see it is expanding in this direction, but it is expanding in the y direction, right? You understood, it is stretched. It is stretched in one direction, contracted in another direction. So both expansion and contraction occurs. Now, how can we include this idea to Hannon map? How will we know whether the Hannon map, 2D Hannon map, is an expanding map or a contracting? Now you know the geometric idea of expansion and contraction of a 2D map. Now I am asking you the question that for the Hannon map, is it an expanding map or a contracting? Yeah, actually, if not greater than 0, if determinant is greater than 1, if determinant is equal to 1, it is area conserving. Area is not changing. If determinant is equal to 1, area will be the same every time you map. Okay. So that's a good idea. Let us go here. So therefore, what we understood from our previous slide is determinant of J is minus P. So modulus of determinant, the area cannot be negative. Area cannot be negative. So we have to take the modulus. Okay. So the modulus is nothing but mod B. Mod of minus B, that is mod B, let us take. Okay. So mod B, if mod B is less than 1, then it is contracting. The map is contracting. Okay. And if mod B is greater than 1, it is expanding. Fine. So if it is asked that for Hannon map, can you find in which region of parameter space Hannon map is expanding, and in which region of parameter space Hannon map is contracting? So you see what is B? Can you tell what is B here? Determinant, but what is the B is a parameter. B is a parameter of the map. So whether the Hannon map is contracting, whether the Hannon map is expanding, all depends on the parameter B of the map. All depends on the parameter B of them, right? So you can say this is contracting, or you can say areas shrink. Okay, areas shrink here, and you can say expanding means areas expand here. Okay, fine. Okay. Now, I hope you guys must have tried in Python already that the Hannon attractor, okay, the Hannon attractor, not all initial condition leads to the Hannon attractor, right? For some initial condition, it will go to infinity. That's what you guys should experiment in your Python code. The initial condition, okay, the initial condition, if you change it a bit, okay, the initial condition, is it always giving you the Hannon attractor? That won't be the case, okay? Some initial condition can give you the Hannon attractor, some initial condition will go off to infinity, okay, diverge. So the question then comes, which initial condition which initial condition can we take so that it guarantees us that this will lead to a Henon attractor? Do you understand my question? I mean, as I told you that some initial condition if you take, it is going to Henon attract. Some initial condition if you take, it is going to infinity. Then obviously one question you should ask me that then it is a very difficult task. For sure, we cannot tell whether this initial condition will always lead to the Henon attractor, right? So how can we make sure that whatever initial condition, can we identify a region? This is the question. Can we identify a region? If you take that region, inside that region, any initial condition you take, it will always lead to the Henon attractor. Okay, that is the question. Okay, that is the question we want to ask. Can it be possible? And the answer to that is yes. Okay, the answer to that is yes. However, okay, maybe I can write it here. I don't have it. But yes, suppose this is the Henon attractor. Let us go back here. Okay, this is the Henon attractor. Actually, you can find a trapping region. Like suppose this is like this. Okay, you can find a trapping region. Okay, this green region, I mean, I can color code if you want. Okay, this is the green region, right? So in this green region, any point you take, okay, any point you take in this green region will always lead you to the Henon attractor. Will always lead you to the Henon attractor. Okay? It is guaranteed. It is guaranteed. However, people have found this, Henon itself found this analytically. I mean, through analysis, he found that this is the parallelogram, okay, where any point you take initial condition in this region will always lead to the Henon attractor. And any point you take outside of this region will diverge to infinity. Okay, that's one of the most interesting part of this. Okay, so but this is known as trapping region. I don't want you to know more about this, but just out of curiosity. So this is referred to as a trapping region. Okay, I mean any initial condition inside this trapping region will give you Henon attractor, and any initial condition outside of the trapping region will go to infinity. Okay, fine. Now we discussed mod b less than 1 or mod b greater than 1. Now what happens when b is close to 0? What happens? So when b is close to 0, you see one phenomenon that is known as strong folding occurs. Okay, strong folding and squashing. Can you tell me why? Can you tell me why? If b is close to 0, we see strong folding and squashing effect. Why? Because when b is close to 0, you are losing invertibility. When b is close to 0, we lost invertibility, right? That we saw in the last slide, isn't it? When b is equal to 0, we saw if b not equal to 0, Henon map is invertible, right? So when b equal to 0, you saw that this comes in the denominator and is a problem, right? So this is what I told you. When b equal to 0, you have loss of invertibility. You have loss of invertibility, and due to that, you see this behavior of folding and squashing. Okay, when the map is non-invertible, you see this folding and squashing effect. Okay, areas fold and repeat and squash. Okay, so that's what maybe your mothers they do while making roti. Okay, I told in the last class. So this is a fun activity I want everyone to try with their mothers. Okay, what is that activity? Like you, everyone is eating roti in home, right? So what you do is take a bowl. Okay, take a bowl. Okay, and take wheat. Suppose this orange is wheat. Okay. Oh, so the blue is wheat. Okay, this blue is a wheat. You make a duff through it. Then you take natural colors. Natural colors means like you take spinach, that is green color. Okay. You take pomegranate, that is reddish color. Okay. Then any other color you recommend? Any other color you get? Milk. Orange color you will get, right? Carrots, orange color you will get, right? Yeah, orange color you will get from carrots. Those different colors you put inside. Green color you put orange color you put, okay, then red color, okay, all this color you put inside your dough, okay, drops, right? And then you mix it. Then you mix it. What will happen? What is your guess? All the colors, if you take a small, if you take, yeah, huh? What? No, from this is the dough, right? Now you take a small chunk. Now you take a small chunk of the dough, okay, and what you will get? My question is, will you get only one color? Mixed. Okay, yes, you will get a mixed color. In any small chunk, if you have kneaded the dough properly, okay, that is a sign whether you have kneaded the dough properly or not. Okay, if you get only one single color, then you have made the dough very good. Okay, in such a way that you cannot make roti out of it. Okay, so the dough is made very bad. Okay, if you have kneaded it very nicely, then in a small chunk of your dough, you will get both red, green, blue, orange, everything inside it. Why that happened? Because all the colors mixed inside the dough very nicely. Okay, very nicely the colors of the dough has mixed throughout the dough. Okay, so this experiment was once conducted by many researchers in a conference to show chaos. Okay, so this is known as kneading effect. This is known as kneading and mixing. So this is known as kneading and mixing. Okay, this is known as kneading and mixing. Okay, so this you can do with milk also. Take a glass of milk. Okay, and what you do, this is the bowl of milk. Okay, and inside that you put some colors. Okay, inside that you put some colors droplets and mix it. What you see? What you see? Those who can do this experiment, share your photos. Share the photos of that. Okay, here. Okay, so it will be very interesting. It will be very interesting because what you expect, what you think will happen. So it will mix in such a way that you will see fractals there. You will see fractals there. Okay. So I hope that I think you guys should do this experiment. Okay. Take any white liquid, okay, which is properly mixing, okay, and put some color droplets there and start mixing it. Okay. So there you will see that very nice patterns has emerged. Very nice patterns of yellow, green, blue, all are mixed. But since you have seen fractals, you can clearly see that those are fractals. The boundaries are fractals. Like it doesn't have a random shape. It doesn't have a regular shape also. It is in between. Not a random, not a regular. In between. Okay. So these are all the ideas. Okay. So what happens if b is less than 1? If b is less than 1, it is an ideal parameter. It's an ideal parameter. Why? This is an ideal parameter because here we see chaos. Here we can see chaos. Okay, we can see chaos. So this is about Hannon map. Okay. So let us return to our question. Let us return to our old question that why study 2D maps? Okay, why study 2D maps? That is the question. So the reason why we study the 2D maps is mainly because of one thing. Okay, what is that one thing? That's what I want you to mind boggle a bit. Then I can say the answer. Yeah. Okay. So the question was, why are we studying 2D maps? Okay. Why are we studying 2D maps? If 1D maps are already there, why we have, and 1D maps are showing all chaotic behaviors, all periodic orbits, everything. So why we need to study 2D maps and increase the dimension and increase calculations and all. Okay. So one of the topics is visualization. So visualization becomes easier as it is, and it is illustrative also. I mean, you can clearly see how chaotic attractor looks like. To clearly see how chaotic attractor evolves and looks like. Okay. And second is the most important behavior, that is about bifurcations. Okay. That is about bifurcations. So 1D maps, in 1D maps, if you remember in 1D maps, what kind of bifurcations have we understood so far in 1D maps? Yeah. Yes. We understood first is saddle node bifurcation. Yes. Saddle node bifurcation, transcritical bifurcation, pitchfork. And one of the most important you are missing, period doubling. That one we saw very clearly, right? Period doubling bifurcation. So these are the 4 bifurcations which you have seen in 1D maps. However, there is one bifurcation which is missing. Okay. And that bifurcation is pretty interesting. Why it is interesting? So before understanding that part, maybe we need to see what is the behavior in each part. Okay. So in saddle node bifurcation, one of the eigenvalues, lambda, will cross +1. If it crosses +1, then saddle node bifurcation happens. If lambda crosses, say, -1, then a period doubling bifurcation happens. Okay. However, in transcritical and pitchfork, usually in symmetrical systems with symmetry, pitchfork bifurcation will happen. Here, what you see from the bifurcation of 1 point, you will see 3 points. 3 points, worth of 3 points. And that happens in a bifurcation like this. It's a pitchfork. Okay. However, in transcritical bifurcation, if you remember, the bifurcation something like is this. Yes. It will exchange the stability. It will exchange the stability here, right? So in all the cases, it is like this, right? However, there is another bifurcation referred to as Nemack-Secker bifurcation. Okay. So this is due to the 2 scientists, Nemack and Secker. Okay. So they found a bifurcation known as Nemack-Secker bifurcation. And what is the importance of this bifurcation? Is this bifurcation only occurs when you have complex conjugate eigenvalues. Okay. This bifurcation occurs when your fixed point or periodic points have complex conjugate eigenvalues. Complex conjugate eigenvalues crossing unit models. Okay. Crossing unit models. What does it mean? That means if your fixed point can have eigenvalues, periodic point can also have eigenvalues. So if your fixed point eigenvalues and periodic point eigenvalues, if they are complex conjugate eigenvalues and they cross, the magnitude of those eigenvalues cross 1 or unity, then a Nemack-Secker bifurcation happens. Okay, this is the condition. Now, what does it mean? Let us start for a fixed point case. Fixed point case. Okay, fixed point case. If so, you will have a stable fixed point. This is a stable fixed point. Yes. What do you mean by a stable fixed point? All nearby trajectory, they approach this fixed point. All nearby trajectory, they approach the fixed point, right? Now, suppose this fixed point has eigenvalues, say, like A plus IB and A minus IB, right? These are the 2 complex conjugate eigenvalues, lambda 1 and lambda 2. Now, as you vary parameters of the system, so as you vary parameters of a system, the fixed point stability changes, right? Fixed point can go from stable to unstable. We saw that, right? Fixed point stability changes as you vary the bifurcation parameter. Now, as you vary the bifurcation parameter, the eigenvalues, complex conjugate eigenvalues, can cross the unit modulus, right? And when it happens, a Nemack-Secker bifurcation will take place. Okay. Suppose that happens. That means as you vary parameter, and at some parameter stage, it crossed mod of lambda crossed unity. Okay, crossed unity. Then what happens is, instead of this fixed point, you will see a closed curve. This is not a curve. But this curve is made with a million of points. This curve is made up of a million of points together, looks like a curve, but it is not a curve. Okay, it is not a curve. Okay, so you can see when this bifurcation occurs, this is known as a Nemack-Secker bifurcation. Okay, now I have given you the idea. Now I will ask you the question, why you think we have not seen this in 1D maps? Very basic question. Exactly. So in 1D maps, you have one eigenvalue. In 2D maps, you have two eigenvalues, right? So since this bifurcation needs to have few complex conjugate eigenvalues, okay? Therefore, complex conjugate eigenvalues means two eigenvalues, a plus ib, a minus ib. In 1D map, can you have two eigenvalues? No. In 1D map, you cannot have two eigenvalues. In 1D map, you have only one eigenvalue. Can it be complex conjugate? No. Complex conjugate comes in pairs, right? So if one eigenvalue is a plus ib, you don't have another eigenvalue to happen, right? In 1D maps. So 1D maps cannot have Nemack-Secker bifurcation. Okay. So this is the idea. So therefore, in 1D maps don't exhibit Nemack-Secker bifurcation. Okay. And therefore, minimum dimension, okay, minimum dimension to showcase, minimum dimension to have Nemack-Secker bifurcation is equal to 2. Minimum dimension to have Nemack-Secker bifurcation is equal to 2. So therefore, maps greater than 2D maps, that means 2D maps or 3D maps or 4D maps and so on, can showcase Nemack-Secker bifurcation. However, 1D maps cannot show it. Okay. So therefore, this is one of the important things to why we studied 2D maps. Why we studied 2D maps is regarding this bifurcation. That is the Nemack-Secker bifurcation. Okay. That is the Nemack-Secker. So therefore, this is one of the most important and very basic concept. Okay. Many of them still confuse that why we don't see Nemack-Secker bifurcation in 1D maps. But why we see Nemack-Secker bifurcation the moment you enter into 2 dimensions. Okay. Because there you start seeing complex conjugate eigenvalues which can cross unit modulus, right? So these are the ideas. So regarding 2D maps, did I show this in last class? Maybe we can have a look one time. So this is interesting chaotic attractors for our case, right? So you can see, yeah. So he is using Python to visualize chaotic attractors. So see, when you are using two-dimensional maps, your chaotic attractor come to life. Okay, how? So you can see what is an attractor. An attractor is a set of values to which a numerical system tend to evolve. An attractor is called a strange attractor if the resulting pattern has a fractal structure. Okay. So you know now why Henon attractor can be called as a strange attractor. Okay, because Henon attractor shows fractal behaviors. As you zoom more and more, you are seeing self-similar behaviors, right? So therefore, you can see it is, so as usual, you cannot have only x square terms and all. You can still have sinusoidal terms, right? So when you have Siderson terms, they are using NumPy. Okay. Yeah, Python is using NumPy, and they're computing this. Okay, very interesting attractor you are going to see. So you can see how this attractor looks like. Okay. I mean, I cannot show it in full screen. Yeah. So you can see this, okay, how this looks like. It gives you a feeling of 3 dimensions, but actually it's a 2-dimensional attractor. It's a 2-dimensional attractor. But you can see this is not regular. The shape is not regular. The shape is not random also. However, it is in between that. Okay. So it is chaotic. It is chaotic. Why? Any point you start, the time series will always be different. Any different initial condition you start, the time series of this system will always be different. Okay. That's one of the use cases of chaotic systems. And therefore, you can use the time series of these chaotic systems anywhere in communication system, secure communication, image encryption, many other places. Okay. So you can see he has colored this same attractor in a density way, right? In a density colored diagram, they have colored it. This same diagram, when you color only black, is just this one. This diagram, when you colored only black points, you get this figure. But when you add density color to it, you get this figure. You see how assigning density color quickly changes the way you explore the patterns here, right? All of these are chaotic attractors. All of these are chaotic attractors. So you see how this chaotic attractor look like. They are always like, you can see, and many mathematicians and many scientists are so dedicated to this that they have created necklace of this shape. Okay, they have created necklaces of this shape. They have created what you call rings on this shape, and they have even have this. Many universities abroad, they have this as structures outside of their university. Okay, a very nice structure, and I mean, we don't understand why this happens till now. Till now, this is an open question. Which kind of equation you can take so that you can get a very nice attractor? Okay, still now it is very open. Okay, so you see many different things are there. Okay, so it can give you a lot of these attractors, lot of the shapes. Okay, I don't think you have seen anything like this before. Okay, these if you ask a art man to do it, it will be difficult. But it can just be done within few seconds in Python or MATLAB or any other coding. So not like this, it can generate very regular structures also. I hope this can give you, this structure reminds you of our galaxy. Okay, this structure reminds you of our galaxies. Okay, so yeah, it is indeed the case. Of course, these are few more regular attractors, and to be honest, I got fascinated, and I have tried myself to do something by myself. I can show you. So yeah, so you can see, like, I did this myself. Like, I was playing around one day, and I started doing these attractors by myself. Okay, to understand how these attractors actually take place. Okay, how these attractors actually come into existence, right? I mean, all are drawn mathematically, okay, using the system, but very interesting plots. And so I had spent around 1 week just doing this. I mean, just enjoying the figures I was getting. Okay, so but I found a pattern. I found a pattern which I was trying to analyze why that pattern emerges, but still I could not succeed. But at least 20-30% I could make it. That always there is a gap here. Always there is a white gap. So wherever you see 0, 0, there is always a white gap. I could not answer why 0, 0 was a white gap. I mean, if I could answer why these white gaps are coming, I could dedicate the structure. I could understand the structure, why it is happening. But till now, I could not understand. Okay. So very interesting figures. Okay. So these are all 2D maps you can visualize here, right? And this is a famous attractor which many people know this is a Bumowski-Mira attractor. Those two people together, they found this 2D system and which can show this attractor, and very interesting here. Okay. So fine. So this is all about 2D maps, which I can tell you about. Let us go back to horseshoe map. Okay. What are horseshoes? So horseshoe is another interesting property. Okay. What is interesting about this? Okay. What is interesting about this is let us do an experiment. Let us do one experiment. This experiment is similar to your roti maker. Okay. I mean, how I told you, put some color in your dough and start kneading it, right? Which color goes where, right? Similarly, you start with step 1. This is the map here. Okay. Now you see I have put one white dot here, right? I have put one white dot here. What you do now is take that and bring it like this, like a boomerang. Take that, stretch it, and bring it like this parallel. So can you see what is happening here? Can you see what is happening here? So you can see the A part has stretched a bit less, but the B part has stretched more, right? The B part has stretched a bit more, right? Then C part again stretch a bit more. D part again the same amount. However, E part again stretched less, right? Now, what I want you to do is again repeat the step. Again repeat the step. Okay. Again take that one. The second step. The second step you have that. You take that one and put it back again. Okay. You take that and put it back again. Okay. So you are slowly trying to see that you are getting noodles shape. You are generating noodles here. Okay. The more and more iteration you apply, it is getting thinner and thinner, right? But however, remember the last case. See the last case over here, right? You have almost all colors distributed in the noodles. You have almost all colors distributed here. See here, you will see at least 1, 2, 3, 4, right? Here, how many colors you see? 1, 2, 3, 4 again. But now you see the colors are distributed, right? The colors are distributed more. Now you see here, they have got thinner, but the colors are distributed even more, right? So quite interesting. So this behavior is known as the horseshoe. Why? Because this looks like the horseshoe, right? Have you seen a horseshoe? Does it resembles horseshoe a bit? The second part. Second part looks like a horseshoe, right? So therefore it is known as a horseshoe map. Okay. Therefore it is known as a horseshoe map. And you can clearly see this is developed by Smale, another scientist, okay, who developed this concept. So he told that if you see this kind of behavior in any system, that is a hallmark of chaos. Whenever you see this kind of behavior, this kind of stretching and folding, so what is happening here? Stretching, okay? So I suggest this is how noodles are made. You know how noodles are made? No? Okay. I will tell you how noodles are made, okay? So you just make a dough. You just make a dough and roll it thin, right? What you do then? Take it into half and again stretch it. Okay. Take those two sides into again to the middle, again stretch it. How many stretch you have? 4. Again take that 4, again stretch it. How many you will have? 8. Again take those 8, again stretch it. 16. Okay. The more and more you do, remember that you have the same material. You have the same material, right? The material will be the same. So only way you can have more and more stretches is through the dimension will decrease, the width will decrease. So from a bigger dough, from a tighter dough, you are entering into noodle shaped dough. That's how you can hand make noodles. Okay. So I suggest you watch some videos which make noodles. Okay. There you will see this hallmark of horseshoes. Anyway, so this is a striking, you can see striking geometric and analytical clarity which describe this homoclinic dynamics. Okay. But why it is known as homoclinic? Because this white part you are seeing here is always there. That is not getting affected. That is always okay. That will be very difficult to shift. Okay, so this is known as homoclinic dynamics. Anyway, so this is referred to as a masterpiece of the mathematical literature, because here you can see, apart from just equations and numbers, you are seeing many things visually, right? So therefore, it is a mathematical masterpiece. It is still worth reading today. Okay, it has its experience till today, and this kind of behavior are referred to as hyperbolic dynamics, which is the next phase of nonlinear dynamics you will study. I mean, if nonlinear dynamics has a next level, it comes in that next level. Okay, these topics. However, we don't want to go much detail here, but I just wanted to showcase this behavior here. Okay, if you want to know more about this, this is the website of AMS, American Mathematical Society, where you can get this more understanding here. What is, they have released a section, what is, so what is a horseshoe? Okay, in that I have taken this image from there. I have taken this image from AMS website. Okay. Now let us go to another map, which is known as a Baker's map. Now you understand why it is referred to as a Baker's map. Okay, why it is referred to as a Baker's map? Because bakers, they bake, they use the dough. Okay, so therefore it is known as a Baker's map. So let us see this Baker's map. It is just a complicated looking mathematical formula. Okay, it's just simple. It is defined in between 0 and 1. It is defined in between 0 and 1. Okay, from 0 to half, you have linear. Again, from 1/2 to 1, you have a different map. The form of the map are different depending on the interval you are in. From z, if x is in between 0 and 1/2, you follow 2x and ay. If x is in between 1/2 and 1, you follow this other mathematical one. Okay. However, what this map does exactly is shown in the figure. You take one smiley face. Okay, that's 2D. That's a 2D shape, right? Can we apply 2D map here? Yes. Because a 2D map you can always apply to a 2D region, right? Agree? Yes. Do you agree? Is it okay or no? Yeah. So when you apply the Baker map, you can see it is flattening and stretching, right? So you flatten it and you stretch it. You flatten it and you stretch it. So can you see B part is happening, right? Then what you do, you cut and stack. You cut in the middle and stack them horizontally. Sorry, vertical, like this. Okay, you got this picture. You do this again and again. So what will happen after 10 iterations? Yeah. What will happen? Yeah, exactly. So to understand this behavior, properly, let us watch this website which shows a video of Baker's map. Okay. So carefully see this diagram here. Okay, so this is a Baker map, and they are using the coding here. Let us see. Yes, exactly, right. So see, every time as he suggested, it will be noodles. Exactly, it was noodles. Okay, so you can see the noodles happening, right? And at one point, you can see the noodles are so thin you cannot distinguish. Okay, so this code they wrote is exhibiting this behavior over here, right? See how it is. So more and more. So you push it down, you scale it, and then you cut it, stack them together. Again and again, you keep on repeating that. That's what Baker's map is. Okay. So this is the starting again. You see, this is the starting again, right? Cut, again, shift it. Right. So we'll restart. Okay. This is the starting. Okay. This is the starting, right? So see how it is evolving, right? See, again it is stretching, again cut in half, and again shift it, right? So you can clearly see how noodles are formed here, right? So I suggest you play around with this. Okay. I mean, understand how they have written this code. Understand how they have written this code, right? So you can clearly see this was my code, right? If x is less than 0.5, you apply one map, else you apply a different map, right? So stretch, why different map? One is responsible for the stretch, another is responsible for the fold. So stretching and folding dynamics you are seeing here, right? So you can adjust here everything. Number of points also you can see how I'm adjusting the number of points. Okay. The less number of points if you do, you can see. Okay. So this is the huge fast behavior you can see here, right? The frequency over here. Let us take more points. Let us take more points. And it is a fast way you are seeing it, right? So quite interesting. So this suggests that when you apply the nonlinear process again and again, you are seeing chaotic behavior, right? You are seeing the chaotic behavior. Okay. So these are all the ideas. You can look into the code. So it's quite interesting how they have written a piece of code which can do all these behaviors and all. And I suggest you go this place here where you can find some data visualization ideas also. Okay. So it is known as observable HQ. Okay. So try to note it down and play around with this. So let us see if we get some other map here. No. This I found it, but can see he has done a lot of things. Okay. He has actually done with this attractors also. Okay. So you see how he's simulating that. I don't know why error are there, but some things are there. Anyway, not working. Yeah, you can visualize a lot of things what he has given here. It's quite interesting. Let us see this one. Yeah. So this is another flow attractor. Okay, this is another flow attractor. I don't know why it is not working. Some errors are already there. Anyway, fine. Okay. So this is all about I wanted to discuss. Okay. So this is all about 2D maps, right? So you can see how 2D maps can be brought to life. Okay. You can easily visualize this. We cannot have in 1D maps, right? In 1D maps, we all had calculations to do, whether it is a stable fixed point or not, right? Anyway, there is one more important concept, that is when a fixed point is stable. When a fixed point is stable, okay. So when a fixed point is stable, for a 2D map, okay. Let us see this, okay. Okay, so you have a 2D map like xn plus 1 is say f1 of xn yn, right? And yn plus 1 is equal to say f2 of xn yn, right? This is a 2D map. And you want to understand the fixed points of this 2D map. So how are you going to find fixed points of this 2D map? So fixed points of the 2D map is given by solving the simultaneous equation, that is x star is equal to f1 of x star y star and y star is equal to f2 of x star y star, right? So once you solve this simultaneous equation, can be nonlinear equation, you can solve for x star and y star. So solve for x star and y star, right? So you will get analytical equations for x star and y star. Now, after you found out the fixed point, your second step is stability. How to know whether the fixed point is stable or not, right? So what you do in for that, you compute the Jacobian matrix. How you compute the Jacobian matrix? So what you do is create a Jacobian matrix here. Jacobian matrix will be formed using this F1 and F2, right? So what you do for this, you take the first element, dou F1 by dou X, dou F1 by dou Y, dou F2 by dou X, dou F2 by dou Y, right? This is a Jacobian matrix. Fine. This Jacobian matrix you have to evaluate in at X star and Y star, right? If you evaluate at X star and Y star, you will get what? Two matrices or one matrix depending on the fixed point. Now this matrix will have eigenvalues. This matrix will have eigenvalues, right? How many eigenvalues it will have? So first of all, this Jacobian matrix is a 2 by 2 matrix, right? So how many eigenvalues it will have? Two eigenvalues. So lambda 1 and lambda 2, right? Based on this value of lambda 1 and lambda 2, you can classify the fixed point as stable or unstable, right? So first condition, if all lambda 1 and lambda 2 absolute value are less than 1, then the fixed point X star Y star is stable. Second, if all lambda 1, lambda 2 are greater than 1, then X star Y star is unstable, right? Third, if say mod of lambda 1 is less than 1 and mod of lambda 2 is greater than 1, then X star Y star is a saddle. That means it has mixed behavior. That means it has mixed behavior, right? It has mixed behavior, right? So this exactly this is the same case and idea as 1D maps, okay? However, geometrically it is very interesting. Geometrically it is very interesting. Now remember, let us go to the next part. Here I will write it. Now that you have got the Jacobian matrix, which is a 2 by 2 matrix, right? This Jacobian matrix will have the trace, isn't it? Trace. What is trace? Trace is nothing but the sum of eigenvalues. Yeah, sum of diagonals. But how can you connect to eigenvalues? This is one of the important properties. Okay, that trace is nothing but sum of eigenvalues lambda 1 and lambda 2. Right? What is determinant of J? These are nothing but product of eigenvalues. Okay, product of eigenvalues. This concept, this idea is really helpful in machine learning. Okay, the trace is sum of eigenvalues and determinant is product of eigenvalues is one of the most important concept in linear algebra. Okay, and is a bread and butter idea. Okay, everywhere you can use this to understand many different concepts. Okay, so now you can clearly see that eigenvalues are related to stability. Eigenvalue are related to stability. However, trace and determinant are related to eigenvalues, right? So can you see a indirect relation? So that means it is telling you that there is a relation between trace and determinant and the stability of the fixed point, right? Because you can see this flow chart here. Trace and determinant are related to eigenvalues. Eigenvalues are related to stability. Therefore, trace determinant are related to stability, right? Got the idea. So therefore, this diagram in the middle presents exactly the same, right? So you can see on this y-axis is the determinant and on the x-axis this is the trace, okay? So you can see here, this is the determinant, okay? This is the determinant of J at the fixed point x star y star. This is the trace of the Jacobian J at x star y star, okay? At x star y star, fine. Now, very nice relation is there that if your trace determinant value falls inside this gray region, then your fixed point is stable. That means inside this region, if your fixed point falls, in all of this maybe I can mark it in blue. Okay. If your fixed point falls inside this region, right, then your fixed point is stable. Then your fixed point is stable. However, if it lies outside of this region, you can see these regions here, maybe here, then it is saddle. Then it is saddle, right? It is a saddle, right? Even here, if it lies, it is a saddle. Okay. However, there is still one more idea. That means if it lies somewhere here, maybe here, you can see these areas, okay, these gray areas, okay, then it is repelling, then it is unstable. Okay, if it is lying here, it is unstable. Okay, this is a very nice geometric interpretation for 2D maps to showcase stability of a fixed point. Okay, now why we have done this? Because for 2D flows, we did a similar idea. Okay, sorry, for 2D flows, we had a similar idea, right? We use trace and determinant here also, right? We use trace and determinant here also to understand the stability of fixed points. So therefore, for 2D maps also, we can have a similar sort of diagram, which can give us an idea about stability of the fixed points, right? So this is the idea, okay? So this is all about 2D maps, okay? More than enough what you should know. So this is all about the ideas of 2D maps, okay? So yeah, all about 2D maps, and maybe next class we can discuss how we can, understand other concepts and take from there. Okay, but it is quite interesting. Okay, this is also known as a stability triangle. Okay, why? Because a triangle decides the stability. Okay, so if your fixed point values of trace and determinant lies inside the blue inverted triangle, then your fixed point is stable. Else, it is not stable. Okay, that's the idea. So this is the ending. What I will give you as an assignment is compute fixed points for the Hanon map and decide their stability. Handwritten assignment for the next class. Okay. Cool. So maybe we will stop here.